Today, we saw at the keynote a nice example of what is FBP and how it's applied in a Node.js environment, the Node-RED. It's quite nice. Everyone could understand what is the flow, what it's doing, and how easy it is. So I'm here. I would say who I am. The challenge and motivation that led me to the flow-based programming. What is flow-based programming? Soleta, the project that I lead, and the pros and cons to that. Okay, I'm a Brazilian guy. I'm a software developer since I was 9 years old, so I'm not that old, but I do software for a long time. And I think in terms of software, more than English or Portuguese or whatever. I work with embedded since 2005. And I started with like my AMO devices, and then I did Tizen for Samsung and Intel and so on. I created my own software consultancy company called Profusion Embedded Systems. It was acquired by Intel in 2013, but this year I'm out to recreate my own company. Okay, I have years of experience with event loop-based programming. If you don't know what it is, I will explain. And I am the Soleta architect and lead developer. Okay, so IoT challenge. If you look at IoT, there is a big difference compared to traditional embedded systems. That was the topic of my research as a manager inside Intel. I had to investigate and see what is different and why it's different. So basically, the difference is on speed of development. Particularly at this point of time where people still don't know for sure what the consumers will buy as IoT, they must experiment. And experiment means faster time to market, it means faster delivery, it means faster everything. So it's much faster than the phones. So when we think about embedded systems, we think about 15 years or more of deployment time, so costs must be reduced. I have years to develop my product because it should last forever. But IoT is like I'm creating a Nest now that should last for 2-3 years, unlike most thermostats that were built to last forever. Okay, so people need speed and people need some ease. We need some guys from the web and from the phone applications to migrate to this new development system. And this is a problem because the web developer doesn't necessarily know what is an ISR and how to handle interruption service, what can be done, what can't. Okay? And the solutions that exist are focused on a single solution. So it's just for hardware access. Like Intel had a nice library called MRAA to access GPIO I2C. And then they created IoTivity that is nice for networking. How do I mix the IoTivity and the MRAA with an HTTP library or MQTT if I want to do more than one protocol in my software? So we need also a scalable solution. In the previous talk in this room, we had IoTivity constrained. There is one API that works on microcontrollers. Then you need to learn another API that runs on Linux. That's not that good because you need to learn 2 APIs. You need to develop 2 code paths. It would be nice to have something that is well integrated where I could reuse my knowledge, right? And that's Soleta. That's a uniform API to abstract platforms, so you know how to upgrade, how to store your files, everything, how to access your sensors, and also how to do networking. Okay, so this is the Soleta project that is the base of this talk and why I came to this. Okay, so we were requested to create an easy-to-use API. To create an easy-to-use API, you must understand your users. Otherwise, your users won't understand your API. Okay, so we started from the basics. Like, how did we learn to program? Like, when we did Programming 101, what was that? And then look at the IoT workflow. Does it match? Like, the IoT lifetime matches to Programming 101? And this is how we start. We read input, we process that data, we finish. We report and finish, right? This is how almost everyone here started to program. Anyone started with a different kind of programming instructions. It's just read data, process it, print, and that's it. Finish your application, right? This is procedural batch programming. It's a single workflow and barely handle any kind of interruptions, errors. It's like you pass the test, no memory freeze, allocations and everything. It's not that good for real life, right? Because when we look at the IoT device, what is the lifetime? We expect to continuously serve multiple inputs at the same time, okay? From network, from sensors, from users, from timers. You may have a coffee machine that is doing like the coffee, so it's brewing, readings from some sensors if I need to make the water hotter, and if the user press the cancel button, or if there is some kind of network maintenance check. There's timers like cleanup timers. Do you want to fire the cleanup timers while you're brewing the coffee? No. So it is hard to make it work with programming one-on-one, right? When you go to novice developers, like freshmen that came out of school and they want to work with you, you say, hey man, how to adapt these to continuous serving multiple requests? It's easy. I do a while one, I'm continuously running, not finishing, it's there, right? I fixed it. Okay, but how about multiple inputs? You're just reading from one input. Easy, sir. We add like lots of functions, one at the bottom of the other. So we read from the network, then we read from sensors. But what if there is a sensor data to be read, but there is no message from the network? You don't read the sensors. It's easy, sir. You go and you check if there is data. Then you continually spin, your battery drains, and your SoC will die sooner, okay? But it's easy to understand, and that's why people come to this conclusion. Also, if process network data is reading from like TCP, and the guy did a huge batch of data to you, you'll be stuck there. So you'll be stuck into process network data or read network input. However, you had a blinking LED or you had an animation on your UI and it stops. And the user thinks that everything is crashed or broken, it will kick the machine, it will complain to you saying that your product is bad. Okay? So there's the last try. We create threads. Because threads solves everything, threads are simple. You basically put the second solution in a thread, right? And I create 3 threads and it's all nice. However, what to do about shared resources? For example, I have a network. I have a UI and I have a sensor. They are on different threads. And the sensor updated. I must update the UI. If you do from the thread, you break everything because the the UI is not usually thread aware. So you run into problems, right? So you stop, you go research, and you find the event-driven programming, also known as main loop. That is pretty common on servers and UI. If you did a UI toolkit, you likely did event-driven programming. Okay? It is super simple because it takes the try tree, but instead of while one, it uses a while wait event. That is where the magic happens. However, the usage, like for the naive developer, it's very simple. You just do a batch of ifs, it's all in a single thread and everything. You may even use a dispatcher table. Like here is all explicit, so if my current event is network, I do this. If my current event is sensor, I do that. Okay, you may convert this to what we are used to in like GTK, Qt, EFL, like register event handler. When there is network event, you call that function. When there is sensor event, you call that other function. It's very easy to understand and people like it. Okay, because it's very similar to 101, so they are used to that. The wait events may handle multiple input and by using a thread or different primitives from the OS. But from outside perspective, from the user, you are looking to it as a simple, single-threaded application. It's very easy to implement with select poll, epoll. Timeout is also an event, so it's very easy to match and add more events like network threads. And it suggests what we call idler. This is a concept where run this function where there is nothing else to run. So this is a kind of cooperative task. Instead of having two threads where one thread is stopped at some random point for the other one to run, instead you have a small function that will give its time to another function and eventually it will be executed again. In more details. So at the top, you can see process network data, the traditional version 101, the programming 101. So when the process network data is executing, let's say it will take 4 seconds because of network input is big. Your LED, your light, is stuck into the on state. So for 4 seconds, the LED is not blinking anymore, right? It's on. And then times the function ends, times kick, LED will be off and on. Then you have double of data coming from the network. Then your LED will be on for double of time, like 8 seconds. So this is pretty bad experience for the user. However, if you break your function into smaller functions, you may interleave with other tasks. For example, turning the LED on and off. So let's say you can segment each function to 1/3 of a second. So you get many blocks, right? They will execute the same thing, but usually it takes more time. As you can see in red, it's more responsive, so it feels faster to the user, but in reality it's taking more time. Take an example like you are painting some line on the screen. So you are drawing pixels. If you segment your work per byte, you know it will be fast, right? But it would take forever because you're throwing away all the cache lines, everything, it will be taking forever. So you need some kind of balance. So the overhead is not that much. However, each of instance is not that big, okay? Because as you can see, there is a space between these two boxes. This is the time to execute these tasks. So there is no magic, right? It's easy to do. Idlers, if you're not familiar with them, they are not that hard to do. If you have original code, there is like a for that you execute the inner block. You move that inner block to another function, right? So you make the original function just a starter where you register the process data idler to be executed when nothing else is being executed. It's like a background task, okay? And when it executes, then you have the context that you use it and you call the actual function, that is the yellow one, the process item. The time of process item is like fixed or short, known to be short. However, on the original code, the count, the number of times that fixed amount of time will be executed is unknown because you're getting that from the network, you're getting that from some sensor, from configuration file. So that is a problem. Then there are pros and cons. Pros, no real concurrency, no need for locks, no deadlocks, okay? It's very easy. It works everywhere. You may get the crappiest OS on earth. If you have like bare metal, it will work there because you don't need any kind of special help from the OS. And it's very lean on memory. If you consider these compared to a thread, here your context is not a full 4K stack, right? It's like one pointer, one integer, and then another point here, right? It's small, so it's very lean on memory. However, it requires you to manually analyze your code, and most people get that wrong, or they are afraid of doing that because you're taking one algorithm, like when there is a simple for, it's very easy, right? But for more complex stuff, it gets out of hand, and most people have problems doing that. You need to maybe recreate your algorithm. It requires callback and extra context, so it's more to remember and more to manage, more to leak, more to crash. The cancellation and error handling must stop the idler and free. Gustavo, this is easy, I know. As you did here, you call idler stop, and that's it, right? But take as in consideration when you read data from a network, and then you decode that data, and then you process it, and then in the middle of that, you get a cancellation. You must know where you are. You may not have just one cancellation. You may have like multiple requests at the same time, like 3 network requests that you are doing in parallel. So instead of a single pointer, you are keeping a list. You must find what to cancel, and it gets out of hand, right? It's painful. So the Soleta project and the initial choices. We had to focus on scalability, so we had to run on very small systems, like microcontrollers. We had lots of previous experience with object orientation in C. We had lots of experience with main loop, event-based programming. I'm an EFL developer myself, so I did that for my whole life in programming, so it was very simple to me, right? And we did networks, sensors, and actuators on top of that. However, as expected, the same design led to the same problems. We had to test if our API was easy enough with random dudes, not just my offs, but some random students, hackerspace, and everything. And we got to the same conclusion that most people don't get callbacks. They get it wrong. Okay, it will lead to segmentation fault, to leaks, and the boring pattern. On event, get some data, do something. It is error prone. Okay, and we could call them idiots and learn how to write code, but we couldn't. So we had to research for a real solution. And investigating, we found the flow-based programming. I wasn't familiar with that. I guess that, who was familiar with flow-based programming here? From where? LabVIEW. LabVIEW? Yes. Okay, it's a good one. Guys from circuit and from electrical engineer are usually more familiar with that. Guys from programming, like who started from COBOL or whatever, we start to learn how to program in traditional batch oriented. But if you look at this, it's easy, right? In this example, I have an action that should be executed on a timely basis that is configured either by a dialer, so you have a dialer where you turn like 5, 10, whatever, or an HTTP server. So here, if you look, it's very easy to understand. If I have a dial input, output, it will be persistence. The persistent data will come back to the dialer, so it's updated, and to the server, so it's also updated. So you feed back the information, and you also change the timer, so it will use the new value, and the action will tick, okay? So mostly everybody gets that, and it's easy to explain even to the non-programmers, like UI designers or your manager. So the flow-based programming was created by J.P. Paul Morrison in the 70s, so it's very old. He says some banks in Canada and things like that use this system, so it's reliable. The idea is that you base your code or your architecture on black boxes, that you don't care what is inside, you just care what gets from it and what it takes. So ports, input and output ports. They produce or take information packets. That's the data, right? The sensor is on or off, if there is a string, if there is a color, if there is a temperature, things like that. It started to gain traction in web recently. So there is this NoFlow. It's a very nice project. It's written in Node.js. But there are also the big guys doing that. So Facebook Flux, Microsoft Event Hubs, Google TensorFlow. And also on embedded systems. If you ever heard about ROS, the robot operating systems, it's all about you have some boxes. So this is the stabilization box, this is the image tracing box, this is the GPS. So you link them all and the robot works. There is a nice one called MicroFlow for microcontrollers and Node-RED, what you saw today at the keynote. Okay, what is the problem with these guys? Like ROS is kind of big, MicroFlow was kind of limited, and Node-RED is based on Node.js, so it won't run on a microcontroller because it's like JavaScript and requires the full Node stack. Okay, the multimedia guys also do that. Video for Linux is a flow-based programming, GStreamer is like that, and Apple Quartz. So concept and terms and our translations to Soleta. So you have the domain-specific language at the top, where you write node 1. This is your variable. This is your instance, right? Officially it's called the process. And you have the type, that is your class, or your node type as we call it. And you have the port, the output port, that is connected to an input port of another node and of another type. So its text description, it's pretty close to the actual graphical description. And it's even easy to convert, so it's very easy to read and to understand. Here, the focus is on the IP, the information packet, or just packet. You don't care what is inside node 1, what is inside node 2. All that matters is that I expect an integer to come from that when it changes. So node as black boxes. It's a very simple interface. It's almost no coupling, or it should be no coupling between the components. One box doesn't share with the other box. All the sharing is done, should be done by the connections and information packets. So that allows you to just replace, like in this, you could replace dial with something. Like in Soleta, we allow you to just replace that with a GTK button. So you could get a GTK spin button, and then you request your peer, hey, you now implement something that delivers that based on a hardware. So I choose C plus GPIO plus whatever. But it's very easy for you to replace. It allows you to optimize code because each port, if it's not used, it could be removed. You can do that with pure C or pure C++, but it's harder. With this kind of analysis, it's easy. You get an FBP, you see which ports are being used, and you can drop all the other functions much easier. It allows for parallelization. That means you can easily move each box to its own process or its own thread. What it takes just you work in the core. It takes no effort from the user because each box is like a black box. So if I'm sending that packet to that box in a different thread or in a different process, it shouldn't matter. We know that reality is a bit harder on us. We have shared resources like underlying libraries. You may have a HTTP node that shares the actual server and socket. So you have some constraints in real life, but the idea is that you could potentially move that to different processes without the user having to worry about that. And also isolation. So you take a third-party model, you are worried about that, you don't want that model to do any kind of ping back home or take too much memory. What do? You easily move that to a different process and put an IPC in place. All that you care is about data. So the IPC is very simple. We offer the IPC using Unix sockets for the basic data types. Okay, so this can increase security. You can apply like SEE or SMAC labels to that process and reduce capabilities, reduce quotas like CPU quota, this quota, even have a different user. And internally, as the node is a black box, you are allowed to use whatever you need. So I need threads. Okay, do threads. The only constraint is that you need to cooperate with the packets and deliver them from the main thread. Okay? And one nice thing is, if an FBP program crashes, it's guaranteed to be the node fault. So the author of the FBP. On the other hand, you can see this from a different perspective. It's impossible for the user to crash your node type if you did proper testing. Taz over there is a friend, and we do lots of EFL development where we call back the user. What happens when the user double free from the callback? It crashes. And he sends you the backtrace and say, Gustavo, this is your fault. Because here we have EFL whatever here, and EFL is your code, so it's your fault. EFL is just the main loop. So it's calling you back. Of course it will be there. It will be in all backtraces. However, the users don't get that. They take time to understand. They did a double free, and trying to find that is hard. But here there is no way to double free or to leak memory. The only thing that they can do is connect where the information goes. So if the information provider or receiver is well done, well tested, then it will never break. That's the same like kernel. If you break the kernel, if you get a kernel oops, it's the kernel's fault. Doesn't matter what you did, if you did a mistake in the user space, it's always the kernel fault. And it's all about information packets. So what goes where? And there is a clear data ownership. The data, like when I do a get, you provide a get of some data, like a get of a string. Who owns that string? Maybe you can annotate that by having a const and having some documentation saying, don't free that memory, it's an internal reference. But users may do mistake. Here, there is no mistake. You create one packet, you put it in the queue, it's not yours anymore. It's owned by the core. So the core will deliver and then will free, no leaks. And the memory management then is hidden in the core. The core is free to postpone, to queue, to reuse packets. Callbacks are also hidden in the core. So if you look at our implementation, it's full of callbacks, but the user won't see them. Like when you send a packet, you are basically calling the callback process of the receiving node. That's a callback, but the user never see that. And packet delivery can be delayed. That means you can put the CPU to sleep or queue that for a while, so you don't busy loop if you don't want to. Packet memory can be recycled, so you can have a fixed pool of packets, and you can even deliver calling or something if your queue is almost full, so you don't overrun in memory. And ports and packets can be typed. That in Soleta, for example. This allows you to pre-validate if it's going to work or not. So you don't need to go and flash and get a runtime error. You can get that in compile time as well. That is something that you may say, yeah, but that's also the case with C. But usually, if you may take a different set of values in C, you usually go with a void pointer and a size or a type. The user may not check that, and there will be a problem because the compiler won't tell you. So you are sending an integer, and I'm getting a Boolean. It will crash, right? So for Soleta FBP, what is specific in it and why we did like that? Basically, we had to focus on scalability from microcontrollers units and up. We had to make it extensible, like microflow was nice, but it was kind of fixed. And we had to focus on configurations because as people are trying to produce more hardware, they are changing the more products, they are changing the hardware. That means that for product A, it's almost like product B, but that changes the sensors. So it still produces a binary, but here's GPIO and here's USB. Okay? So we had to be careful with these configurations and allow easy configuration. For more details, you can look at Ivan's study. It's flow-based programming on our wiki. Okay, but going for the things that matter, we are statically typed. Why? Because we want to have more information to optimize on small MCUs. We still don't do all the optimizations that we could, but we run very low on memory. So I can share with you that we have an OIC with Zephyr running in 100K of flash, 32K of RAM total. So the user didn't write one single line of C code, just an FBP, OIC client, GPIO for LED and a button, and it will work with not that big overhead. That means like IPv6, UDP, OIC, CBOR, all the overhead that the networking technology brings. We type check at both compile and runtime. So we have an FBP generator and FBP runner that I will show you how they are used. We check at both. We have a series of predefined packet types, so Boolean, integer, string, direction, vector, color. But we also allow you to pack them in a single unit. So you have 3 integers and 1 string. That's okay. You can pack them together into composite packets. And of course, you can provide domain-specific packets like I have an image, I have a sound, I have an MIDI, things like that. You can create your own packet. You don't need to serialize an image to a series of color packets. So packets are immutable, and thus they are read-only. You cannot change them. That allows us to deliver the same packet to multiple connections, because that's an extension that we created as well. So you may be connected from multiple ports, if you're an input port, and you may be connecting to multiple output ports. So this is one nice thing that we do. On send, the flow core owns the packet. So it's not yours anymore. You don't need to care about memory management anymore. We are going to do that for you. Each deliver happens on a different main loop iteration. So if you have a feedback loop like this is a feedback loop, right? From dial, persistence, and then back. If you do this naively in C, it triggers an infinite recursion. It will blow your stack. But we don't have that problem because each function is called from the main loop. So the stack is kind of low, and you can do these feedback loops very easily. We also, as I said, allow multiple connections to and from ports. And the ports can know who is connected by providing the connect and disconnect methods or callbacks. So these allow for things like I have 32 ports and the user just connected 2 ports. Should I wait all the 32? No, I need to wait just for 2 ports to provide a result at the end. So you can use connect and disconnect to do things like this. And of course, if you are taking packets, you must provide the process function that is your entry point. This is per port, not per node type. Okay, so some solutions, they queue all the packets for you, like they put in an array, and they call process, and then you pick from each box. In our solution, you are called for each of the packets that come in. You're free to reuse or do that internally if you want, but this is how we do. So the usage workflow, you may write your own C code, then compile, and that's the canonical execution. Or you create a source flow-based programming, that is the DSL, that you can use together with a solveflowboard.json. That is a per board configuration that I'll show you. And from that, you have 2 paths. One, you can generate code. Then this generate file is just like this one and goes to the final binary. Or you can execute it, just like JavaScript or like Python. This button is only available on powerful systems like Linux. You need more memory, you need introspection, things like that. Here at the top, we just generate the what we call resolved information. So there is no Node.js or there is no JSON parsing in here in the generated source. There is no string. when you see out in this binary, in this source and this binary, there is no out written in it. We resolve that to a port index. So the dispatching is pretty fast. We have, at the end, 2 arrays. One array is of the node types. So this is my objects. You create it like this. These are the options, and this is the type. And then you have a connection table, like a telephonist, where you say object 0, port 0 goes to object 2, port 1. And that's what you get. So it's very simple and it's very fast to execute. Okay, and the configuration. It's a unique feature from us. The idea is that you can generate configuration files per application, per board, and per application and board. You also have a fallback here, so you can provide things to test on desktop, for example. This is the case when you have a board with a GPIO that is a given number. The second board is a different number of GPIO. The other board is not even GPIO anymore. It's a keyboard. And then you want to test that on your PC. Then you want a GTK button to show where you can press and it will simulate for you. With this configuration file, it's very simple to do. It's automatic. You just have to create a JSON file, say the name, say the properties, and that's it. You can run, or you can use that configuration file in the FBP generator. That is useful for cross-compiling. So I'm compiling for a board with Zephyr and ARM board, but I'm running from Linux. I don't want it to use the Linux file, so you can manually specify. And it's even auto-detected. If you're running on Linux, it will use a series of JSON, regular expressions from a JSON file, and it will detect this is a BeagleBone Black. So these are the sets that I should be using. This is an Intel board, so these are the settings that I should be using. It's very neat. Our node types or components, what goes in here in blue. So they are very simple. They are a C structure, or a pointer to a C structure with an open and close. That's basically the constructor and the structure, and an array of ports. That's it. It's very simple interface. It's very simple to write bindings, to reuse these objects even outside of Soleta. You can use a libsoleta.so, so you can have like a timer. It's a built-in node type. It's inside libsoleta. Or you can create an external .so that Soleta will find automatically based on the name. Or you can put that into your application. You don't need to install that on your system, or in the case of static linked applications, you use this option. The descriptions or meta information, what is the port name, what is the port type, this is all compiled. You can compile that out. So on microcontrollers, you are not getting that information, you throw it away. Okay, and you use the FBP generator to resolve that into C code, and then you just compile it, or you use the FBP runner. That is very easy to use. You can try it like you do in Python or Lua or Node.js. You can even create meta types, or you can create types by using meta types. We have a type that allows you to, a meta type that allows you to create based on FBP. So you use a FBP as one box into another FBP. That is easy to split your code and organize your code. You can create the meta types for composite types, so how do I split and how do I merge them? And even JavaScript, you can create a node type written in JavaScript. And we also have node type options. So the traditional versions of FBP do something like this. They call initial packets. So you have a node here, like a GPIO, and you want to set the pin number to 1 and active load to true. We convert that to 2 options. The first option is to specify the options in the node, and the second one is to create a configuration file, as I told you before, like my GPIO. And then when you run, it says, what's my GPIO? I don't know. So I will look into the configuration file. So The environment variable matched my board one, or the regular expressions matched my board one. Then it will pick the my board one and will look, oh, my GPIO, it is a GPIO reader with pin set to 1 and active low set to true. Okay, so you don't need to change your FBP at all. You just reuse your FBP with different configuration files. Including on desktop, you may use the GTK or keyboard and console to make it easier. Okay, and this external configuration is something that we like very much, because we had to deal with Zephyr boards running, Intel Quark SE boards running Zephyr, and we had to manage some Minnow board, Galileo, BeagleBone Black, all the kinds of Linux boards, and they were all different in pin numbers and everything. So the cons, paradigm shift. It is very hard on experienced developers. If you're used to think about procedural programming, regular object-oriented programming, you are going to have problems, I won't lie to you. We all had when we started. It was new to all the developers, so we had to learn it, and we did lots of mistakes. The biggest mistake was trying to synchronize things that are not synchronous. For example, we have a node here, node there. They are exchanging one information. Information inside that pipe, inside that connection, is synchronous. However, if I had two objects providing data to the same object, if this data was generated before that data, it doesn't mean that this data is getting in before. It may be reordered across channels, across connections. Just inside one connection, it's guaranteed to be linear. And why that was a problem? Because people start to do hacks like, oh, I have this node and I have another and then another. So this adds a hop. It will delay the packet delivery, right? So this one was like a straight line, so the packet arrived earlier. So what people start to do, let me add a hop here just to delay and let me synchronize it. And then boom, because that delay may be like a bigger node that will delay for 3 iterations, not just one. So it was us getting it wrong and learning with the mistakes. So the paradigm shift, it's not that easy on experienced developer. However, if you get the naive developer, the freshman, guys from non-computer areas like kids, they get it right. And they're not stick with the information and to the paradigm that we are. And it requires bindings. So if you want to use another library, you have to integrate that. It's not automatic. It's not like include the C file and that's it. You need to create a node type, and you do that in C, of course, and you need to expose this manually. It's like doing a Python bindings or Java bindings or Lua bindings. We do add some overhead. There is no magic. There is no free lunch. But we believe that the overhead is not that much. It allowed us to run on very small boards already. And you need a balance to see what you're going to write in FBP and what you're going to write in C. Clear example, we started with the basic node types, like this is a addition, this is a multiply, this is a comparison, this is an and that's it, okay? So let's write Fibonacci. Fibonacci, canonical example, should be very easy, but it's not. It's very easy to get wrong. And then you start to look and lots of mistakes, lots of people trying. First, it's not simple and it's not efficient, because what should be a straight algorithm in C using all the registers, you are now creating packets, sending packets, queuing, going back to the main loop, so it's not efficient. However, it is easy to get it wrong and do things that you should be doing in C, in the node type, trying to do as an FBP. Sometimes it's valid because it's just a proof of concept, you're just experimenting, then you can do that. But you need a careful balance to see what you're going to provide in node type and what you're going to use in FBP. The pros are much bigger in our understanding, and that's why I'm here. We have no leaks, no segmentation faults, reduced blaming. It's just by itself, it's worth. But also, it makes it easier to collaborate across teams. So if I need to create an API and give it to you so you can implement, it's not that easy, right? People get it wrong, you're dictating my design and so on. This is not the coding style. But here, the interface is, these are the data that I get in, this is the data that I get out, that's it. So in the case of the dialer, here, I may just use like an HTTP server again, or I may use a keyboard or something. And I give it to you and say, hey, go and implement that using I2C, SPI, I2C, GPIO, whatever. I don't care. This is my contract. I want an integer in, integer out, and that's it. Okay, so it is very easy to collaborate with different teams. It's also very easy to read, write, and visualize. We even have a tool to convert to GraphViz, so you can get a plot. We don't have a visual editor like Node-RED guys, as they do. We would love. Some people even started it, but they abandoned that. But anyway, and it's very fast to prototype and to test. So as developers, we started to use FBP more and more to test our code. First, FBP, the inner code must be asynchronous. So when you design the API, sometimes you miss that. So you have to review in the next iteration. If you try to do the binding for FBP, you get it right. And then you get the benefit, it's much easier to test. So we have lots of tests in Soleta code and lots of samples that you can use as a base to learn Soleta. And that's it, thank you. You can check our OIC tutorial at the GitHub. It explains to you how to create, to very simply create a switch and a lamp using OIC with Soleta. So 0C code is just putting together some FBP, nice drawings and some explanations, even on how to read the errors, like if you did a mistake, if you did a typo, then it explains to you how to read the error messages and all. We also have, I don't have in this talk, but I had in a previous one, a tool where you can have a Node.js application to run on board. Then you get the browser, you type the FBP, and you can run. Of course, you can run our samples without having to install Soleta on your PC or your cross-compile to your board. Okay? So, one question. Someone has a question?
Thanks for the presentation. It's really inspiring. I wonder how do you in your system you will have some events that will come from outside that may be concurrent from GPIOs, IOs, whatever. If I understand correctly, you will do some some nodes to handle them, and then it goes to the FTP. But at one particular time, how do you manage the concurrent realm and the interface between this concurrent realm and the non-concurrent realm? I mean, is the API in between thread safe or whatever? What's the...
Okay, so mapping that to flow. The flow is not meant to be doing, at least our implementation of flow is not meant to be doing real-time tasks. Okay, so what Soleta does? Soleta is a project, not just the FBP. We use a main loop internally. So all the interruptions, we queue to the main loop and dispatch later. So everything is dispatched to the user, like, I don't want to use FBP, I think it's crap, but you do have a nice abstraction layer, like it's a glib or a Qt for IoT. So you run code on Contiki, Riot, Zephyr, and Linux, okay? I want to use that. You are never called from ISR. We queue that, so it's delayed. So what we recommend, that drivers, like I have a component, you do the drivers in the kernel, if it's Linux. If it's another OS like Zephyr, they are taking the same approach. They have a sensor framework that is like a sensor subsystem where you can use that. And you can provide stuff in there, like a thermostat and things like that. So you do it there. What you expose here is high level. So if you think about a company, you have guys that are creating the business logic, guys that are creating the drivers, guys that are creating the actual subsystems. So these guys provide libraries to each other, like the drivers guy provides some libraries to this guy, writing the node types, and I'm just linking the blocks together in a very manager and designer understandable way. So it's all about macro blocks. Okay, you are not doing like the driver in FBP itself. You can try to do that, but there are no real-time guarantees and nothing. So you may run into problems. However, for a quick test, maybe it's doable. So we don't block you doing that, but it's not the recommended way. Does that answer your question? Okay. Another question? Someone? No? Okay, another one.
You mentioned that one node can send to many other nodes. Do you support one that the message goes to all the other nodes, or just one, some kind of load balancing, or both? Or
the way that we do is you need explicit connections. And what we do is we have an array, and we walk that array from the main loop. So it's like this. I'm at index 0, and index 0 is your node. So I will get the packet that guy sent a packet. I put in my queue, like sending queue, and I check this packet must be sent to this and this guy. This one is you. So I say, hey, it's your time. I call your process function. You process that. You are not allowed to keep a reference or modify that node, that packet. You may clone that. You may copy it. When you return, I'm going back to the main loop. So if there are some events like network stuff, I will do. And then I will go to the next one. If you send some packet, that will be queued, right? So I'm not looping from you to you again. I give the time for the other guy, and then I'm back to you. So this is how it's done. I have this Soleta, this other presentation that will also be online. Here I have more details and even an explanation what is the FBP syntax in more depth. Okay, and the size, like what's the size overhead. It's not just our overhead, right? Because this includes the OS with micro IP, UDP, 6LoWPAN, radio drivers, GPIO driver, and everything, CBOR, CoAP. But you can see it can be very small and efficient. So a peak of 32K. This hardware had 80K of RAM. So, and in this hardware, nobody could run the JavaScript in it. So we really think that JavaScript is another great solution. That's why we want to allow you to write some node types in JavaScript, particularly for prototyping. So as I said, I can define the node type writing Node.js or in JavaScript, and then I send to experts, go optimize this. Measure, take like months. I just need 2-3 days to do my prototype, and then you take months to optimize that. So it is a good approach. Okay, and I believe it's time out, so we can go drink some beer. Thank you, guys.